So next, we can go to the more deep into the subject. So the more technical side we can discuss now. So for that, we have to start with the wave equation. Okay. Again, the wave equation is the wave equation basically represent the wave equation of electromagnetic wave inside the nonlinear optical media. So the governing equation for the electromagnetic wave is the Maxwell's equation that is already known to us. Okay. So which are the Maxwell's equations in media? We can just list down the Maxwell's equation in media. So in general, the Maxwell's equation we can write in this way: del dot D equal okay, it need not be zero. Del dot D equal to rho F, and del dot B, it is always zero. So I am putting tilde means it is an oscillating quantity in general, because in the wave equation that we are going to discuss here, the nonlinear optics, we are actually involving the field which is oscillating in nature. So that is why I'm putting a tilde over everywhere. And what about the Faraday's law? The del cross E become minus dou B by dou T. And the last equation would be del cross H equal JF plus dou D by dou T. Okay, again JF can have tilde. So this is the Maxwell's equation in general in case of any media. Okay, so I'm not considering whether it is linear or not. Okay, so this is general representation of Maxwell's equation. Okay, now to simplify our discussion, we will assume certain things. So the first assumption what we are making is there is no free charges and there is no free currents. Okay, so we are setting JF is 0 and rho F is 0. And also we are assuming the material is non-magnetic. If the material is non-magnetic, the magnetization M would be 0. Okay, then we can write H simply become H can be written as B upon mu 0. So in general, H would be B by mu 0 minus M, where M is called magnetization. So remember the general expression for H was B by mu 0 minus M. Since M is 0, the H simply become B by mu 0. Okay, so if you use all these approximations or all these assumptions, then what would be our Maxwell's equation? So then Maxwell's equation becomes del dot D becomes 0 and del dot B, it is always 0, and del cross E become minus dou B by dou T, and finally del cross H can be written as del cross B by mu 0. So mu 0 can be taken to the right. So del cross B equal to mu 0 dou D by dou T. Okay, now we'll try to derive the wave equation from this set of equations. So what is the usual step to derive the wave equation? It is a very easy way to do it. So just take the curl of any curl. Okay, so just take Del cross of del cross C or del cross of del cross B. It's up to us. Okay, so better I will take the del cross of the curl of this equation. So curl of del cross E, that will become minus dou by dot T of del cross B. Okay, so here the one thing we have used, the time derivative and spatial derivative is always commutes in case of the electrodynamics. So that is when in usually electrodynamics it commutes, and hence we have just interchanged the expression. Okay, actually the del cross comes on the left side, but you can take del cross to the right side also because del cross and dou by dot T commutes. Now del cross of del cross E can be written as del of del dot E minus del square E. That would be equal to minus dou by dot T. Del cross B is mu 0 dou D by dot T. Now del dot E is 0. Okay, how come del dot E is 0? Because del dot D is 0. And that will give the implication of del dot E will be 0. Okay, so we can set del dot E 0. Then what we'll get is minus del square E equal minus mu 0 dou square D by dot square. Okay, good. Now what is this actually capital D? So capital D is epsilon 0 E plus the polarization displacement is epsilon 0 E plus P. Now the polarization we can divide into two terms. We can have a linear term, which is simply epsilon 0 chi 1 E, and plus it can also have a non-linear part, which depend on E square, E cube, etc. So this the linear part of the polarization is simply can be written as epsilon 0 chi 1 E. Okay, so this would become epsilon 0 1 plus chi 1 times E by combining the first two equation plus the polarization of nonlinear. Okay, so then our equation become minus del square E equal minus mu 0 epsilon 0 1 plus chi 1 E. So this epsilon 0 1 plus chi 1 we can write as epsilon R to the first order times E plus the polarized nonlinear polarization. So dou square D by dot T square can be written as epsilon 0 epsilon R 1 dou square E by dot T square plus dou square P nonlinear by dot T square. So what would be the final expression? You can take this term to the left side. So therefore the equation become minus del square E plus mu 0 epsilon 0. Now mu 0 epsilon 0 is something but 1 by C square. So instead of mu 0 epsilon 0, what we can write is 1 by C square we can write. So the numerator only we can write epsilon R1 divided by C square dou square E by dot T square equal minus mu 0 dou square the nonlinear polarization divided by dot t square. Okay, so this would be the wave equation satisfied by the electric field in nonlinear media. So this is the wave equation. So better we can take this the entire thing to the right side for further discussion. Okay, now if you look at this wave equation, suppose if nonlinear term is zero. Okay, suppose the medium is linear. The medium linear means the nonlinear polarization would be zero. Then this equation would be simply become del square E equal epsilon R1 divided by C square dou square E by dot T square. So this implies that the speed of the wave in the this nonlinear in the linear media would be simply equal to C by square root of epsilon R1. Okay. Now what is this equation? This equation is three-dimensional wave equation, isn't it? So this is the three-dimensional wave equation without any source, without any source term. Okay. So there is not okay. So this is a simple wave equation or a free electromagnetic wave. So basically, we can write it as a three-dimensional free electromagnetic wave equation. So this shows that we'll get a normal electromagnetic wave in the linear media. So it will satisfy all the conditions of electromagnetic wave in vacuum. Okay, the only difference is it will have the speed which will be lesser than c. The speed of the wave would be equal to c by square root of epsilon r1. On the square root of epsilon r1, we can identify it as refractive index. So this can also be written as c by n, that is n equal to c by v. So n is a refractive index. So what would be the expression for refractive index? So the refractive index is square root of epsilon r1. So for the linear media, the refractive index of the medium would be equal to square root of epsilon r1 if the material is non-magnetic. Okay, so there is a case. Okay, so it's very simple. Now, okay, so that means if the medium is linear, we will get the normal electromagnetic wave. There is no problem. Now, what about for non-linearity? So if non-linearity is present, then there will be a right side, there will be a non-zero term. So that actually represent a source term. So this gives an additional oscillation to the electromagnetic wave. So depending upon the frequency of polarization, it will generate the new electromagnetic wave of the new frequencies. Okay, so that is why we have earlier we have said that if the polarization is oscillating with frequency omega, it will generate frequency omega. And similarly, if the polarization is oscillating with frequency 2 omega, it will generate frequency 2 omega. Now, this is a general expression. It is not frequency, not fixed here. So what we can do is we can expand this electric field in Fourier series. It can be the superposition of many frequencies. Okay, so in general, the electric field E we can write as sum over n E n e raised to minus I omega nt. Then correspondingly, the nonlinear polarization and that can also be written as sum over n Pn. Pn is a function of omega n e raised to minus I omega nt. If you substitute it here and simplify it, we can show that the each component of the frequency has to satisfy the same equation. So therefore, the equation satisfied by the particular frequency component of electric field and nonlinear polarization become dou square, it's a del square En plus epsilon R1 divided by C square dou square En by dou T square equal minus mu 0 dou square Pn. It is a nonlinear part. Okay, so better here we can use superscript here divided by dot T square. So we can further simplify this. We can change mu 0 into epsilon 0. So what we can write is it can be written as minus del square En plus epsilon R1 by C square dou square En by dot T square equal minus 1 by epsilon 0 C square dou square PNL of N divided by dot T square. Okay, so that means we have got the wave equation in nonlinear media, nonlinear crystal. Okay, so next, using this wave equation, it is possible to show the generation of the some frequency on difference frequency or the second harmonic, etc. in general. So that would be the most general way of doing things, and we can also show the phase matching condition as the implication of this wave equation. Okay, so for the time being, we can stop it here. So what we have done is we have derived the wave equation satisfied by the electromagnetic wave in nonlinear media. So the left side contains the electric field strength is the nth component of electric field. That is what we have written here. The En is the amplitude of the nth frequency or omega n frequency. Okay, the En is the component of e raised to minus I omega n. So okay, so it is a component of omega n frequency, and similarly Pn is the component of omega n frequency. So what we have written here is frequency specific. It is for omega n, and this is for omega n. Okay, so so this is for a particular frequency. So next, what we'll do is using this equation, we'll try to show the possibility of some frequency generation or second harmonic generation, and the requirement of phase matching condition. Okay, so we'll discuss in the next class. So see you then.